All right, let's go through activity 7 where we're working with the launch data set again, trying to predict the profit of a newly released product based on some anonymized predictor variables. So as always, I'll load up reg class so that I can use all the commands, and I will load up the launch data. And in this case, since there are so many predictor variables, I'm going to make our lives a little bit simpler by just looking at the first 10 predictors. So we'll try to predict profit from the x1 through x10 variables. And so essentially we need to extract the first 11 columns of the launch data frame and name it something else. And so that's what this command right does. Takes the launch data frame, it leaves the row space blank because we want all the rows, and we just want columns 1 through 11 here, and we name it PL. All right, so let's start out just by fitting a multiple regression model predicting profit from all 10 predictors. No interactions, nothing fancy going on. So we can do that just by doing M left arrow and then LM and then the formula for our model. And in this case, since we're predicting profit from all the variables, I can do the twiddle dot shortcuts and just specify the data frame where that lives. And then I'm going to want a summary of the model. So I fit the model, run the summary, and I'm asked to report what the value of r squared is for the model, and that's what r refers to as multiple r squared, so 0.7015. R squared adjusted is 0.6968. And finally, the root mean squared error, the typical size of the residual, R calls that the residual standard error, so that is 0.2831. So typically it looks like the actual profits of these products are about 0.28 units away from what the regression would predict. And we might wonder if we do any better, if we get a better model, by incorporating interactions. Because very often the relationships going on between the predictor variables and the y variable are complex. Very often the strength of the relationship between y and x actually is not a constant, which is what our multiple regression model here assumed, but it actually depends on the characteristics of the other individuals, the other variables. So it's always a good idea to explore the possibility that interactions may be present. And so we're going to run this line that fits the regression model with all 10 predictors and all two-way interactions. That's what this twiddle dot squared shortcut is. It essentially says, all right, predict profit from all the variables in your data frame as well as all two-way interactions. All right, so let's get a summary of this model and see if we did any better. So we see there's a lot of output, a lot of predictors in that model, and we see that the value of r squared has increased to 0.7777, but that's no big surprise. We know that every time we add a new predictor into a regression model, the r squared is going to get bigger, regardless of whether or not those predictors are related at all to y. And so a fairer comparison of how well the model fits the data is the r squared adjusted, which we see is 0.7572. So it's actually increased substantially by about 0.05 by adding in these interactions, so this model is definitely doing better. And the root mean squared error here, the residual standard error, 0.2533, that's giving us the typical error the regression makes when predicting the profit. So it's decreased from about 0.28 down to 0.25. So that might not seem very much, but it's actually a pretty big decrease. If we look, this decrease is about 0.03, and that's about 10% of the root mean squared error of our original model. So by incorporating those interactions, the typical error the regression is making has decreased by about 10%. That's pretty good. So the model with interactions has improved. The r squared adjusted has gone from 0.7 essentially to 0.76, and that's a pretty big increase. And what we saw is that the root mean squared error here has decreased from where it used to be at about 0.28 to 0.25, a decrease of about 10% here. So our model is about 10% more accurate in terms of how far away those predicted values are from what they actually are, and that's a pretty nice thing. All right, so that interaction model is definitely an improvement over the model with no interactions. And so let's look at some of the interactions that might be important. So let's go ahead and scan through all of our interactions. So these predictor variables up here on top are just the variables by themselves. So this would be the coefficient of just x1, this would be the coefficient of x4, etc. And these are the coefficients of the interaction variables. So the predictor variable defined as the product between x1 and x3. So since there are so many predictors, it's not really a good idea to use 0.05 as our reference for what is and is not statistically significant, because just by chance alone, we're going to get p-values less than 5% sometimes. 5% of p-value should be less than 5% when there's nothing going on. And so we're going to be a little bit more stringent and say that, all right, let's make sure that it has a very small p-value before saying that it's statistically significant. So which one of these interactions are have p-values less than 0.001? Well, these stars kind of give a guideline. The more stars, the more significant that interaction is. And so we see that the interaction between x1 and x3 has 3 stars, but it's still bigger than 0.0001. So scanning down, here's one that looks like is highly statistically significant, x2 and x3. Scanning down to the next 3-star one, nope, that's bigger than 0.0001. These guys, though, between x5 and x8, and between x5 and x9, those look to be statistically significant according to our new criteria. And, all right, so last one is x6 and x8. And there we go. Those are the ones that pop out just by scanning down that list. And basically what that's telling us is that if we had a model with all those other predictors, including all those interactions, except for the x2, x3 interaction, actually adding in the interaction between x2 and x3 to that model, significantly reduces the sum of squared errors. All right, so let's examine the relationship between profit and these two variables specifically, as well as their interactions. That was one of the more important ones we saw. And so let's go ahead and fit this model. I'm going to call it m.23. And the way that we do this is do our y twiddle, and then we can do a shortcut for both predictors and their interaction by separating the two predictors by a multiplication sign. We'll say where that data lives, and we'll run visualize model to look at what the model implies about the relationship. So here's the key skill that we want to develop is how do we actually talk about what these plots are revealing about the nature of the relationship between these three variables. So first thing we do note is that the interaction term is statistically significant. Adding the interaction into the model to the model just predicting based on x2 and x3 significantly improves it, decreases the sum of squared errors. So this interaction is definitely statistically significant, and from the look of the interaction plots, it's also very strong and important because we see that the nature of the relationship between profit and x2 or profit and x3 seems to actually change quite a bit depending on the value of that other variable. These three lines look quite a bit different here. All right, so when we do have a statistically significant interaction, one of the implications is that the expected difference in y, in this case the expected difference in profit, between two products that differ in x2 by 1 unit is no longer a constant. It actually depends on what the particular value of x3 is of the two products I'm comparing. So what we're going to do is we're going to talk about that by looking at the plot on the right. And so we're asked, all right, when x3 is near 0, are the expected differences in profit between products that do differ in x2, relatively small or relatively large, and then at values of x3 near 150, are the expected differences in profits big or small? So, all right, let's hone in on values of x3 that are close to 0, so right here. So drawing an imaginary vertical line, we see that as we compare the differences in profit between individuals with small, median, and large values of x2, we see a relatively noticeable spread here. But as we move into comparing products with x3 values of about 150, we see there's a much larger spread in the profits between individuals with small values of x2, median values of x2, and large values of x2. So overall, we see that the difference in the profits based on the different x2 values is relatively small when x3 is close to 0, but the differences are really quite large in profits based on their x2 values when x3 is large up near 150. All right, so when x3 is near 0, the difference in profits between products that vary in x2 is relatively small, still noticeable because we see from going from the smallest value of x, or one of the smallest values of x2 to one of the largest, we do see some noticeable difference in profits, but it is relatively small compared to when x3 is 150. So this is relatively small compared to the difference in profits between products that vary in x2 when x3 is near 150. So for small values of x3, if we compare products with small values of x3, we see a relatively small variation in their profits between small and large values of x2. And when we compare products that have very big values of x3, we see a pretty big difference in the expected profits depending on x2. There's a big difference between small values of x2 and big values of x2. All right, so one of the implications is that when we look at the difference in profits between two products that differ in x2, it actually depends on what x3 value I'm actually honing in on. And the other implication of a significant interaction is that the strength of the relationship between profit and x3 depends on the x2 values of the products I'm comparing. The strength of the relationship between profit and one of the predictors isn't a constant, but it depends on what the value of the other variable was that was involved in the interaction. So we'll once again look at the right plot. The right plot shows us the relationship between profit and x3. And these three lines show us the relationship between profit and x3 for three different values of x2. So when we look at individuals with small values of x2, the relationship is described by the blue line here. Basically, we see no relationship between profit and x3. It's essentially a flat line here. Regardless of the x3 value, it's the same value of the profit throughout. Now the story changes when we start looking at individuals with median values of x2. In that case, the relationship between profit and x3 is given to us by the black line. And we see that when we look at individuals with median values of x2, the relationship between profit and x3 is noticeably positive. This line is sloping up and to the right. And then when we look at individuals with some of the largest values of x2, we see the relationship between profit and x3 is even stronger. The slope is even more positive. So what is the story that the interaction plot is saying is, okay, well, as we compare individuals with progressively larger values of x2, essentially going from the blue to the black to the red line, we see that the strength of the relationship between profit and x3 is getting stronger because the slope starts out at about 0 and just keeps getting more and more positive as we compare individuals with progressively larger values of x2. So, all right, what we want to answer is, does the relationship between profit and x3 strengthen, weaken, flip sign as the x2 values of the products grow progressively larger? So what we see is we see that the strength of the relationship between profit and x3 grows progressively stronger as we consider individuals with progressively larger values of x2. These aren't really individuals, these are products, so I'm going to change that. So in other words, the relationship between profit and x3 is very weak for products with small values of x2. That's that blue line. While the relationship between profit and x3 is strong and positive for products with large values of x2. That's that red line. Okay, so when we do have a statistically significant interaction, we always want to look at these interaction plots to see if it is an important or a strong effect. And that's exactly what we do see here. We see a very strong effect. We see that the nature of the relationship between profit and x3 changes in character quite a bit depending on the x2 values of the products that we're honing in on. For small values of x2, there's really no relationship between profit and x3. For products with large values of x2, we see a very strong relationship between profit and x3. We could ask the question the other way around, how does the nature of the relationship between profit and x2 vary depending on the x3 values of the products we're looking at? Well, we see that for products with small values of x3, this blue line here, the relationship between profit and x2 is positive. But as we consider products with progressively larger values of x3, going from the blue line to the median to the red line here, all the way up to products with the largest values of x3, we see that the strength of the relationship between profit and x2 gets stronger. So initially, the relationship starts out positive. The relationship between profit and x2 starts out positive for small values of x3, and it only grows in strength as we consider products with progressively larger values of x3. All right, so question 4 now asks to see if there are any influential points in the data set, because we know that not all points have the same amount of influence when determining what the regression model looks like, and it's a good idea to make sure that we don't have any data errors going on. So what we look at is the influence plots of the model, and in this case we're looking at the model with all the interactions. So we'll plot this, and I'm going to make this a little bit bigger here. And what this plot attempts to do is look at two measures of influence simultaneously. The leverage of a point is how unusual that point is in terms of its combination of predictors, its combination of x values. Larger leverage means more unusual, and only points with a large leverage have the potential to be influential. And we also look at the point's deleted studentized residual. Now remember, this is basically the residual made by the regression model built on the data without that point. And so values bigger than 2 or smaller than -2 indicate that that point is pretty far away from where that regression is predicting when you build that model without that point. So it's kind of far away from where that regression was going. So influential points live in the top right rectangle and in the bottom right hand rectangle, and in this case they're indicated by black X's through the circles. The sizes of the circles vary because they are coded proportional to the Cook's distance, kind of an overall measure of influence. The larger the circle, the more influential. And so we see a lot of X's here. We see a lot of influential points, and so that's something that we need to investigate. We need to make sure that these points are actually valid. So when we run influence plot, if we look at what's underneath the $sign leverage, this gives us the row numbers of those influential points. And the first thing we're being asked is how many points are influential. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points here. All right, so let's look at one of them here, the point on the very far right, this guy right here, the one with the highest leverage, the most unusual in terms of its combination of predictors, happens to belong to row 463. So let's actually look to see if we can identify what makes this observation unusual. It might be unusual in one or more predictors, or it may be unusual in some combination of predictors. And so let's just look to see, well, what are the summary statistics for all our predictors, and what does this particular row look like? So let's extract row 463. All right, so one way that we can attempt to glimpse what makes the observation unusual is to compare the individual's x values and y values to the overall distribution of the values in the data frame. And we just look to see, okay, well, does it happen to be maybe one of the largest or the smallest observations with respect to x1 or x9, etc. So the profit was 5.9, which is on the higher side, but definitely not on the very outskirts. X1 is a little over 3 million, so kind of right in the middle there, a little bit above the 70th percentile. X2 was 8,700, so a little bit on the larger end. X3 was 44, kind of right in the middle there. X4 was, 4.7 million, so a little bit on the high side, but not the biggest. X5 was 11, so a little bit on the small side, but not the smallest. X6 was 0, which is the smallest value, but you see that the median value is also 6, so over 50% of the observations had X6 values of 0, so not very unusual. X7 is 5, so a little bit on the lower end, but not the lowest. X8 was 551, a little bit on the higher end, but not the highest. X9 and X10 were both 2, so on the lower end of those variables, but not the most unusual. So what we're seeing actually is that this point doesn't really stick out in any particular predictor or in y. It doesn't have the largest or the smallest values, so it must be unusual in some combination. and it would actually be very difficult to flesh out that combination. We'd have to look at all the pairwise scatter plots, or might even be unusual in terms of a combination of 3 or more variables, in which case we can't really visualize it. So it's a good thing we have this influence plot, because this point doesn't look all that unusual in terms of its predictor or y variable, but the analysis is indicating that, hey, it actually does have more than its fair share of influence on those regression coefficients. So what we see is that we don't see anything particularly unusual with this point, because it has fairly ordinary values for each of the predictors and for profit. It doesn't have the smallest or largest values of any of them, with the exception of x6, but over 50% of the data points had an x6 equals to 0, so that's not unusual. So this point must be unusual in some combination of predictors. Okay, this question now deals with fitting a polynomial model. And if you look to see a kind of a regression or a scatter plot predicting profit just from x2, you do detect a little bit of a hint of nonlinearity. So I'm going to name a model M2, just predicting profit from x2. And we're going to visualize this model, just so you can see what I mean here. So visualize model M2. We see that, okay, maybe there's a hint of curvature going up this way. There's that hard-coded minimum value of profit. That's kind of a weird feature in the scatter plots. But we might be better off by actually fitting a curve to this relationship, a polynomial model, instead of just a linear model here. So what we're going to do is we're going to take the model we just fit and run choose order. Oops, not choose model, choose order here. And what that will do is it will try out a bunch of polynomial models from order 1, just the simple linear regression, up to order 6, basically predicting profit from x2, x2 squared, cubed, fourth, all the way up to x2 to the 6th power. And so here's what those curves look like for the various different orders. And here are the summaries of those models. And so what we're going to do is we're going to compare the models r-squared adjusted. And we know the higher the r-squared adjusted, the better that model is fitting the data. And if we scan down, we actually see the highest r-squared adjusted is at an order 3, basically predicting profit from x2, x2 squared, and x2 cubed. However, we would prefer a simpler model if we can get away with it. We prefer not having as many powers of x if we can do that. And so the guideline is to choose the smallest order, whose r-squared is still within 0.005 of the absolute largest value of r-squared. So in this case, 0.005 smaller than 0.504 would be 0.499, and we see that the second order polynomial meets that criteria. Its r-squared adjusted isn't too much smaller, and it's simpler because it's only second order here. So we will go with the second order polynomial here. All right, so it looks like I've already written this comment here. So nothing new. It looks like that second order polynomial is the best fit. Its r-squared adjusted is much higher than just the order 1 polynomial, just the simple linear regression. So a big improvement over the linear regression. And going to the order 3 polynomial doesn't provide enough of an improvement for us to want to use it. We want to go with a simpler model here. So all right, let's fit this model now. So let's fit a model predicting profit with all interactions and include the relevant polynomial term in x2. All right, so pretty complicated looking model. Let's figure out how we do this. So I'm going to say m, I'm going to name it polyint. And all right, we want to predict profit from all variables and the interaction. So twiddle.squared will do all predictors and all interactions. And then we also want to add in a polynomial term in x2. So we take out the x2 term, and then we add in the polynomial model in x2, poly x2 comma 2. And we say that we're working from the PL data frame. And we can run that model, and then we can get a summary of it to see, all right, does adding in that higher order power kind of help out our model here, scanning all the way up and down. Here is the coefficient of just x2 in the model, and here's the coefficient of x2 squared. And we see that, yeah, it is statistically significant. Yes, the p-value is 9.14 times 10 to the minus 6th power. And we can ask ourselves, okay, well, it's statistically significant, but do we get a big improvement in terms of the fit? Well, the r-squared adjusted now is 0.7647, and the root mean squared error is 0.2494. How did that compare to our previous values of r-squared adjusted and the root mean squared error? Well, we see that without that polynomial term, the r-squared adjusted was 0.757, so a little bit of an improvement. That's kind of nice. And the residual standard error, the RMSE, has decreased from 0.253 to 0.249. So has the model improved? Yes, the model has improved. But we see that the improvement is relatively minor. It's not a huge improvement, but it looks like we're doing a better job at describing the relationships. All right, question 5 deals with adding a new variable to the data frame, because very often the variables provided to you aren't the actual best predictors of your y variable. So we're imagining x3 and x9 might be the number of advertisements for this product shown on CNN and Fox News. And if x1 is the number of people who saw just some internet ad for the product, then what we could do is take the ratio between x1 and the sum of x3 and x9, because that would represent the total number of people per ad, essentially. So we might expect the profit to be related to that, the number of people per ad that saw the product. And so let's try to predict the profit from this particular predictor here, x1 over x3 plus x9. So how do we do that? Well, we're going to start out by defining our new variable. We're going to call it PPA, and that is just x1 divided by x3 plus x9. Now, if I just put it like this, it's going to give me an error because it says, hey, I don't know what x1 refers to. And that's because it's living in the PL data frame, so I actually need to refer to that by PL $x1. That extracts the column x1 from the PL data frame, so I'll do that everywhere here. And so now I've defined a variable called PPA, and I want to add that to the PL data frame. So the way that I do that is give the name of the data frame, then a $, and then the column name that I want it to have in that data frame, and I'm just going to call it PPA. And we're going to put our newly defined variable in there. So we're going to take the values in PPA and we're going to put that into a new column called PPA in the PL data frame. And now let's try to predict profit from PL, from that variable here. So I'll do m.ppa, lm profit, twiddle PPA, data equals PL, and we'll get a summary of that model. Okay, so is this term statistically significant? Well, we look at its p-value, and yeah, it is. So yes, the p-value is 8.27 times 10 raised to the minus 13th power. So it is a statistically significant interaction. The sum of squared errors decreases by much more than just adding a predictor that's unrelated to profit. And so it is a highly statistically significant regression. Now, is it a strong predictor of profit? Well, looking at r-squared, no. R-squared is 7.6%, so knowing this person per ad variable only gets you about 7.5% of the way there to knowing the profit. So it's not a particularly strong predictor, but it is a worthwhile predictor to consider. Maybe, adding this to the model with the interactions could actually help to improve it. That's worth exploring, but we won't do that in this activity. All right, question 6 deals with extrapolation, and in a multiple regression context, it could be difficult to tell if a prediction requires extrapolation because a new value might have fairly ordinary values for x, but it could be unusual in some combination of two or more of those predictors. So let's go ahead and define a data frame called 2.predict, which gives the x values of two new individuals. So the x1 through x10 values for individual 1 look like this, and for individual 2 look like this. And we'd like to know, okay, do either of these predictions require extrapolation? Are they at unusual combinations of x that haven't been used to build the model? So when we run extrapolation check, this number right here tells you the fraction of values in the data set used to build the model that were closer to the center of the predictor data cloud than the point in question. So here, observation 1 here, this first individual for which I want to make that prediction, it looks like it's farther away than 99.8% of the individuals actually used to build the model. That's pretty far away, so it's pretty indicative of an unusual combination of x's that I'm making a prediction at. And so I would be worried about extrapolating for observation number 1. Now, individual number 2 here, if I look at the number here, it's 36.5. So that means it's only farther away than 36.5% of the data values used to build that model. And so it's really not all that far away. There's probably other combinations of x's that were seen when building that model. They're fairly similar. So I wouldn't be too worried about extrapolation here. All right, so do either require extrapolation? So observation 1 requires extrapolation, most likely, because 99.8% of the products used to build the model are closer to the center of the predictor data cloud than this product. So this product must have a pretty unusual combination of predictor variables. And so if we make a prediction there, that assumes the model is going to extend to that combination that it hasn't really seen before, and by very nature that's extrapolation. So we'd be worried about that for observation 1. All right, so we're finished with activity 7, so I will compile that and get that up on Blackboard.